for this webinar, we will be discussing scientific methodology. And the chapters that are incorporated for scientific methodology, Module 1, you will be looking at Chapter 1 and Section 2.2. Section 1.5 of Chapter 1, you will be reading within your biology e-textbook. Hopefully, this lecture will help you to understand the following. At first, we will be starting off with a brief history of the advances in science. Then we will discuss mathematics and the importance that it has and how it's integrated throughout conceptual integrated science. I will give you a definition of what we mean by inquiry-based science. And from there, we will discuss the scientific method, or more recently called the experimental design in its totality. From there, I will give you some examples of what a good hypothesis is versus a weak hypothesis. And then we will move on to talk about the entire scientific experiment as far as collecting data and the two types of data that can be collected within a science experiment, qualitative versus quantitative. From there, we will discuss the difference between facts, theories, and laws, and how science has its limitations. We will move forward to discuss the integration of science and other facets, such as art and religion, and how that can be integrated, and learn how technology as well has forward our advancement with science. We will end this webinar by, I will be giving you a brief overview of what some of the concepts that you will be discussing within the next 9 modules in regards to our natural science course. Just a quick few tips for when you're doing your chapter readings within your ebook. Keep in mind that the textbook is not a novel. You do not want to read the book from cover to cover. In each module, it is giving to you the chapters and the sections that apply to the concepts that you will be learning. Also keep in mind that the book will only tell you something only one time, and try to maintain your focus by stopping and restarting frequently. This is a lot of information that you will have to retain for this course. So don't feel bad if you have to take a break from your reading and then come back. Also make sure to take notes using your course of study and the guiding questions that are embedded within the modules. This also will help you and provide a nice study guide for you before you take the objective assessment. So here are some questions that I want you to think about as we go through this module. Science is all around us. It is the product of observations and rational thinking. It is a method, a way of discovering the order within it. And it's also a skill that must be learned and a tool for solving problems. So we're going to talk about exactly what is science, or why is it that we think about science the way that we do? Where did it originate? How should we use it? And what would everyday life be like without it? Sometimes these are not the type of questions that we think about in our everyday life, but hopefully this course will provide you with a solid foundation and open up your minds to more to engage in science and see how it is applied in our everyday life. So, the word science, where did it come from? It is derived from a Latin verb meaning to know. It developed out of our curiosity about ourselves, out of other life forms, the world, and the universe. So that is where that term science comes from, because you want to know about the things that's going on around the world. Science helps us to understand why is it that we had tsunamis that occur naturally? Why is it that we have earthquakes that occur naturally around the world? So science is trying to find out what events cause which results. Trying to figure out the cause and the effect in the world around us is basic science. This is rational thinking as it is applied to the physical world. What caused that recent tsunami in Japan? What caused that hurricane to occur the Hurricane Katrina in Louisiana? So, what causes these events to happen? Some of these answers you will get as you study throughout the modules for this course. So we will begin with section 1.1 and how it will show how some of the advances in history has occurred from our past to our present. So the beginning of science goes back thousands of years. Keep in mind that we did not always have experimentation as we know of it today. Rational thinking was not relied on, but people relied heavily on superstition and magic to interpret the physical world around them. There are still cultures to this day who rely heavily on witch doctors. So keep in mind that centuries ago, thousands of years ago, rational thinking was not used. Experimentation was not used to understand the world around us. What was used was basically observations. And based on those observations and the known intellect is what we perceived science to be. So the ancient Greeks used logic and rational thought to investigate the world around them. And they were responsible for making many of our earlier scientific discoveries. The ancient Greeks learned that the earth was round and they helped to determine its circumference. They discovered why things float. They learned the rotation of stars throughout the night is due to the rotation of the earth. And they also get credit for finding the science of botany. And what is botany? The study and classification of plants. So if you are a scientist that studies plants, you are considered a botanist. Moving forward, when the Romans conquered Greece, they adopted the Greeks' mode of scientific inquiry. And there's that term again that I will be discussing with you more in later slides. When the Roman Empire fell to nomadic tribes, all scientific advancement halted in Europe. So this is when religion is starting to become more established. Now, just because science advancement halted in Europe, that didn't mean that it halted in other parts of the world. So at that time, you had the Chinese and the Polynesians who were charting the stars and the planets. The Chinese were looking for the elixir of life. Back in those days, instead of it being called chemistry, it was called alchemy. And during those times, alchemists were trying to find that immortality to life. Arab nations developed mathematics and learned to make glass, paper, metals, and certain chemicals. So all of this was going on during the Dark Ages in Europe. So this is why certain knowledge was lost as religion became more established during Europe at this time. Now, it was during the 10th through 12th centuries that we have Islamic people bringing books into Spain that had once been banned by the church. This is where scientific inquiry is starting to re-emerge itself, and universities are emerging as well. So during the 15th century now, as we're moving forward, you have the invention of the Gutenberg's printing press. And when this printing press was invented, science made a huge leap forward. People were now able to communicate with each other across distances. So what does this mean about science? We were able to make observations and share this discourse with others around the world. Up until the 16th century, for example, people thought the earth was at the center of the universe and that the sun revolved around the earth. Well, Nicholas Copernicus challenged this theory, and his ideas were banned for over 200 years because it conflicted with the ideas of the church, which brings me to experimentation. It wasn't until Galileo who was an Italian physicist who gets credit for being the first person to use experimentation to validate rather than to speculate. And I will talk more about that in a few slides ahead. The arrival of the Renaissance period provided a foothold to the advancement of science and rational thinking. Because keep in mind, with that example that I led into with Nicholas Copernicus, if you went against the grain of the church at this time, your ideas were conflicting and you were banned. So it was not until Galileo revived the Copernican view, and what happened with him? He was later arrested as well because he also conflicted with the views of the church. So scientific discoveries are often opposed, especially if they conflict with what people believe. Every age had its intellectual rebels if you look at the history of science. And it was these intellectual rebels who were persecuted, condemned, or suppressed, but later were regarded as harmless and even essential to the advancement of science. And going back and mentioning Galileo, even though Copernicus was banned, for his idea of the sun being at the center was banned for over 200 years, then Galileo reviving it, and then he was arrested for that. But look what happened. It turns out they were correct. The sun is at the center of our universe. So oftentimes during the time, these individuals who were once deemed rebels actually were harmless and very essential to the advancement of our scientific knowledge. So just to give you a quick little recap, forward steps in history of science as highlighted in your e-text occurred in Greece first, then Italy, China, Polynesia, the Arab nations, Poland, Germany, and of course in many other parts of the world. Moving forward to section 1.2, section 1.2 discusses mathematics and how it is integrated within science. Mathematics is an important tool in science, and you will use some math in this course, but primarily doing your physics portion. So you would generally be introduced to the types of mathematics that's integrated within science in your forces and energy module, modules 2, and also in discussing scientific concepts within module 1. If any of you are also involved or enrolled in our INT 1 or INT 2 course, you also will be utilizing some mathematics skills with your summative task as you will be collecting data, which we will be discussing a little bit further along in this webinar. So science uses equations, mathematical equations as shorthand notation for the relationships between scientific concepts. Math abbreviates a relationship that can be stated in words. It helps to make common sense of our science, okay? And these equations help to guide your thinking to make draw rational conclusions when it comes to observations and analyzing your data. So moving into the scientific method, or the experimental design, you may have heard of this term before. It is a classic tool that is outlined in section 1.3, and it is utilized to help make sense of a science experiment. The scientific method is not to be memorized, but is one of the ways good science is performed. And more importantly, it helps you to acquire that attitude of inquiry and the use of experimentation and replication. And it allows you to have a willingness to accept findings, even when those findings are not desired. So we're going to talk now a little bit more about the scientific method. But before we get into that, I want to discuss this term inquiry. And what do we mean by scientific inquiry? Because inquiry is at the heart of science. There are 5 essential features that characterize inquiry, and I have listed them here, and I will discuss them now in pretty much of a nutshell. Inquiry helps a learner, and you being the researcher, you're the learner researcher, you are engaged with scientific questions. So you have this scientific question that you want to find answers about. And you're going to give priority to the evidence that you have collected as you plan out your procedure for conducting this investigation on this question that you want to find the answer to. So, inquiry will help you as a researcher to develop your descriptions, which is your observations, and explain and predict using evidence about your scientific question. Inquiry will help you make connections from your data that you have observed, that you have collected on your question, and to make those connections to draw a good conclusion for that scientific experiment. And once you have done that, you can write your science report. And that report is allowing you to engage in this discourse and communicate to others how you clearly outlined your procedures of this testable question and how you collected evidence or data. And then you provided explanations as to why your experiment came up with the results that it did. So inquiry is all of those facets put together. Having a scientific question, designing an experiment to test that scientific question, answering questions, making observations, collecting data, and then analyzing that data and putting it all together to come up with a valuable and a valid conclusion. So there are 2 main processes of scientific inquiry. We have something called discovery science, and this is mostly about describing nature. Let's say, for an example, I put a box in front of you, and I tell you to take your time and just discover, just go through the box, go through what's in the box, and make observations and describe what it is you're seeing. You are learning from your observations, based off of observations. And this is more kind of like a discovery science. A hypothesis-based science is mostly explaining nature. You are just like I described in the previous slide. You are developing a hypothesis and making predictions, and you're going to do an experiment to test your hypothesis. So most scientific inquiries combine these 2 types of research approaches. For INT1, your summative task, you are going to be using the hypothesis-based approach because you have to formulate a hypothesis. And then you have to test your hypothesis, collect data, and come up with your results. So section 1.4 gives you the definition of what a scientific hypothesis is. And it is exactly what is stated here. It is an educated guess. A hypothesis is a concept that has yet to be verified, but if proved true, would explain certain facts about specific phenomena. Okay? All hypotheses must be testable. And we're going to talk about the principle that incorporates that meaning in a second. Here's an example of what I mean by testable. Atoms are the smallest particles of matter that exist. Well, if you have sat in on my live webinar on matter or listened to the recorded chat on matter, you would know that matter is anything that takes up space, that has mass and takes up space. Matter is everything around you. And atoms are the basic units of matter. So we can test this. And how can we test this? By using a special electron microscope. And we can see that atoms are the smallest particles of matter that exist. So this could be considered a hypothesis. So here's a quick little test. Which statements are scientific hypotheses? I'll give you a few seconds to read it over. A, better stock market decisions are made when the planets Venus, Earth, and Mars are aligned. B, Atoms are the smallest particles of matter that exist. C, Albert Einstein was the greatest physicist of the 20th century. Or D, the moon is made of Swiss cheese. If your answer stated A, B, and D, you are correct. A may not be considered a plausible hypothesis, but it can be tested. If you notice when the planets are aligned, Venus, Earth, and Mars, and wait for those planets to become aligned, and then you take a look at the stock market and see about decisions that are being made, you can test that hypothesis out. We already talked about B and how that is considered a scientific hypothesis. C, Albert Einstein was the greatest physicist of the 20th century. Well, that sounds like that's an opinion, and we cannot test that. So that would not be considered a scientific hypothesis. The moon is made of Swiss cheese. Yes, we can send someone to the moon. NASA can do that, and we can take samples of the moon, so that can be tested. So A, B, and D can be considered scientific hypotheses. So let's try this question, doing it and asking of you in the opposite manner. Which of these is not a scientific hypothesis? A, protons carry an electric charge. B, undetectable particles are some of nature's secrets. C, charged particles will bend when moving in a magnetic field. Or D, all of the above you would consider to be scientific hypotheses. So once again, which of these is not a scientific hypothesis? Well, if you answered B, you are correct, because once again, that is an opinion. It's too subjective and it cannot be tested. So let's talk about what I meant by a weak hypothesis. Here's one here. Temperature may cause leaves to change color. It is this single term here, or this single word here, may, that causes this hypothesis to be considered weak. When you are formulating your hypothesis, you want to stay away from words like may. You want to try to be more definite in what you feel or what you believe. So you would say temperatures do cause leaves to change color, or you would say temperatures do not cause leaves to change color. Here is a very strong or a strong way to write this hypothesis. If leaf color change is related to temperature, then exposing plants to high temperatures will result in change of leaf color. Sometimes this is called an if-then statement. And this is a very strong hypothesis because you are telling me that you do believe that color change is related to temperature. There is no room for questions. And then you will go and you will design your procedure to test out this hypothesis. So this would be considered a strong hypothesis because you have made a stance. So let's talk about this principle of falsifiability. For a hypothesis to be considered scientific, it must be testable. It must, in principle, be capable of being proved wrong. And I talked about that a little bit prior with examples. That is called the principle of falsifiability. So, a well-known scientific hypothesis that turned out to be incorrect was that of the Greek philosopher Aristotle. Aristotle claimed that heavy objects naturally fall faster than light objects. And why did people believe Aristotle? Well, keep in mind what I mentioned earlier on. Its science was not always based on rational thinking and experimentation, rather based on the known intellect of the time. And Aristotle was a known intellect of his time. And he did not believe that heavy objects naturally fall faster than light objects. And so people believed him. And this hypothesis was considered to be true for nearly 2,000 years, only because he was a great thinker of his time. And also, you want to consider the fact that air resistance was not considered as an influence on how quickly an object can fall. But then came along this gentleman that I mentioned prior, Galileo. And it was through Galileo's careful examination of Aristotle's hypothesis that changed science forever. It was Galileo who climbed to the Leaning Tower of Pisa and experimented with this hypothesis, and he showed the falseness of Aristotle's claim. This caused a huge advancement in experimentation now. No longer are we thinking to go by just to believe in something just because it was stated by the known intellect. So for example, here's another example. If you were driving down the street and your car broke down and Einstein was walking down the street and you said, "Hey Einstein, my car broke down, what's wrong with it?" And maybe Einstein knew nothing about cars, but you knew who he was to society. And he would take a look under the hood and say, "Oh, I think it's the carburetor." You would believe him. Well, Galileo stopped that because he finally did experimentation. So let's talk about what we mean by experimentation. Here on this slide, section 1.5 goes into the scientific experiment in details. And I just placed a few of my favorite quotes dealing with experiments. My most favorite one is the one here by Albert Einstein. Can you tell that I am a huge fan of Albert Einstein? "No number of experiments can prove me right. A single experiment can prove me wrong." Love it. So keep in mind, when you're doing experiments, you have formulated your hypothesis, and your experiment tests whether your hypothesis is true or false. It is important for your experiment to be a fair test. And we're going to talk about this because this is when variables come into play. You conduct a fair test by making sure that you change only one factor at a time while keeping all other conditions the same. You should also repeat your experiments several times to make sure that the first results weren't just an accident. That is replication. Okay, so we'll talk a little bit more about these now. So what is a variable? You have three types of variables. You have your independent variable, your dependent variable, and control variables. Your independent variable is defined as the factor being manipulated. Your dependent variable is defined as the factor whose outcome is being measured. And your control variables help to account for other variables that might threaten the internal validity of your experiment. So we're going to talk about some of these in a little bit more details with some examples. This first example, I want you to read through with me, and then we will talk about identifying the different variables. Henry and Eliza conducted an experiment using plant fertilizer. They added different amounts of fertilizer to 7 pots of bean sprouts. The pots were the same size and had the same type and amount of soil. They were given the same amount of seeds, light, and water. To find out how the fertilizer affected the growth of the sprouts, Henry and Eliza calculated the average height of the bean sprouts in each pot. Here are the factors from their experiment. So your independent variable here would be your amount of fertilizer. And why is that? Because that's what they were changing. That's what they manipulated. See here, they added different amounts of fertilizer to see which fertilizer will cause the bean sprouts to grow. Which brings me to your dependent variable, which is the average height of the bean sprouts. That's your measurable effect. So your dependent variable depends on what you're changing in your independent variable. The controlled factors here are your size of pots, amount of light, amount of water, amount of soil, and your number of seeds. Why are those considered your control factors? Those are considered your control factors because those are the variables that needed to remain the same, or the factors that needed to remain the same so that it would not adversely affect the rest of your data. So for example, what if you were giving different amounts of light with the 7 pots, as well as different amounts of fertilizer? How would you know if it was the fertilizer or the light that affected the height of the bean sprouts? You wouldn't know. So it's important to have things that are controlled within your experiment so it won't adversely affect your data. The only thing that you want to affect your data is your independent variable. So let's try this. I'm going to give you some time to read over this next example, Krusty Krab's breath mints, and I want for you to think of the control group, the independent variable, the dependent variable, what a good conclusion would be, and we'll talk about conclusions more a bit further. So let's read through this. So now, which people are in the control group? If you answered group B, you are correct because nothing was happening to group B in this example. Group B is the comparison. That is what Mr. Krabs is going to use as a comparison. So that would be our control group. A control group and control variables are two different things. So what would your independent variable be? If you said the secret ingredient in the breath mint, you are correct because that is what he's changing. What's our dependent variable? If you stated the amount of breath odor or bad breath, you are correct because that's what he's measuring. And what do you think Mr. Krabs' conclusion should be? Yes, the breath mint does reduce the amount of breath odor more than half the time, but it is not 100% effective. So for this conclusion, or for any of your conclusions when doing a science experiment, you have to draw your inference based on what data you collected. You cannot just say, yes, breath mint does reduce the amount of breath odor, because it didn't happen in all of the here and in all of the groups. It was effective, yes, but it was not 100% effective. So in saying that, why do you think group B reported having better breath? The placebo effect, of course. So one thing I want you to keep in mind is that this above example is considered a qualitative experiment, which is not acceptable for INT1 or INT2 task 3. Because it is qualitative. Mr. Krabs was basically going off of measuring breath odor. There was no numbers involved here. So keep in mind that for your summative task for this course, you do need to be able to collect measurable data. Do a quantitative experiment. So as you're doing your experiment and you're collecting data, observations is very important. And what does that term observation mean? Observation is the use of senses to gather information, either directly or indirectly with the help of scientific tools. So while conducting your experiment, you are constantly making observations as you are collecting your data. And your recorded observations, that will be considered your data. There are two types of data, qualitative data that Mr. Krabs collected, and quantitative data that you need to collect for this course. Keep in mind, for INT1, you have to record measurements. So anything dealing with length, volume, density, anything time where you're collecting numbers is considered quantitative data. And you're going to organize that into a data table and a graph. Qualitative data, what you just saw with Mr. Krabs, is in the form of recorded descriptions rather than numerical measurements. And in your e-biology book, they discuss an example with Jane Goodall. And they show you how she spent decades recording her observations of chimpanzee behavior during field research in the Gambian jungle. And she documented her observations with photographs as well as movies. So once again, this is qualitative type of data. She went out and did a field study and recorded her observations from there. So here's another example. Let's try this one. This is called Super Bubbles. Nick and Nandi love to blow bubbles. Nick found some Super Bubble soap at Cellmart. The ads claim that Super Bubble soap will produce bubbles that are twice as big as bubbles made with regular bubble soap. Nick and Nandi made up 2 samples of bubble solution. One sample was made with 5 ounces of Super Bubble soap and 5 ounces of water, while the other was made with the same amount of water and 5 ounces of regular bubble soap. Nick and Nandi used their favorite bubble wands to blow 10 different bubbles and did their best to measure the diameter of each one. The results are shown in the following data table on the next slide. So let's take a look at what their collected data will look like. This is, of course, a quantitative data, collecting quantitative data, quantitative experiment, because they're measuring the diameter of their bubbles. So here we have it, an example of their data table. So your data table should always have a title as well as your columns here. Here they did 10 bubbles, and here is the Super Bubble results, and here is the regular soap results. So your quantitative data is recorded as measurements, and then you're organizing them into a data table. This is what their graph would look like because, well, one example of a graph that they can construct could look like this. When you are doing your science experiments, you always have a data table and a graph that coincides with your data table. Your graph is a pictorial view. So when you're drawing your conclusions or you're using inductive reasoning, you're deriving generalizations based on a large number of specific observations. So for this bubble example, you would summarize their findings and either accept and refute their hypothesis. This example here of this graph, it does not depict the total calculated averages, but you could do that. That could be a different way to show this data. You could calculate the average and graph the final number, and then you would have a double bar graph. And if you look back at the results will be Super Bubble, I believe, was 15.1 centimeters with the total average, and regular soap was 11.5 centimeters because we measured it in centimeters. So what should their conclusions be based off of this graph? The Super Bubble solution did not seem to produce bubbles that were twice as large as those made with the regular soap. Although the average size for the Super Bubble solution was larger than the average size for the regular soap, but it was not twice as large as the ads claim. In fact, only 2 of the 10 trials had results that will fit the ads claims. So you have to report it, whether or not it went for or against your hypothesis. You have to report the truth and what your data is showing you. Now, let's talk about reliability or validity. Would we consider Nick and Nandi's results reliable? Why or why not? One thing to think about is the description does not say who blew the bubbles for each solution. And the two children could blow the bubbles differently and could have a different strength in blowing the bubbles differently. So that would add some adversity here in our data. That would have us question how reliable this graph is. So there may be difference in bubble sizes due to the person blowing the bubble rather than the bubble solution. You don't know. They might have considered having each person blow 5 bubbles with each solution. So you have to keep that in mind when you're discussing reliability and validity. One other thing I want to point out with this graph is here. Always remember to have a title for your graph and make sure to label your Y and your X axes. Now here you want to put the metric units. You might want to put in parentheses centimeters so that we'll know what these numbers stand for. Okay, so that's also important to have your units after your labels as well. So your conclusions summarize how your results support or contradict your original hypothesis. Keep that in mind with your science report. So just to do another quick overview of the scientific method, you are going, or the experimental design, you're going to ask a question. You're going to do some background research. What's the literature say about this problem that you're trying to solve? From there, you're going to construct a hypothesis. Then you're going to test it with an experiment. You're going to collect your data and analyze your results to draw a reliable conclusion. Is your hypothesis supported? Is it confirmed? Or do you refute your hypothesis? And then you're going to report your results in the format of a science report. And from there, you're going to replicate it and start all over and do it again, just to make sure that the data that you collected the first time was not an accident. And that's basically what happens within science in its totality. It takes years for the FDA to approve something for human consumption. So it's very important that you realize that the medicine that's on the shelves now is still being tested, even when it has been approved. This is how we learn about different side effects. So this is how you are applying science with our everyday world. Section 1.6 moves on into talking about the difference between facts, theories, and laws. And basically, this slide gives you the definitions of each one of these terms. I am going to be talking a little bit more in detail about theories in the next couple of slides. But an example of a fact is the limb of an amputated salamander. If you know anything about salamanders, and if you cut off their limb or their limb comes off in the fight and flight response, it can grow back. That is a fact. It is a fact because it's a phenomenon about which observers can agree. We can see that. It does happen. A theory, an example would be atom bonding and formation. When you have the bonding of ionic and covalent bonds that you learn in Module 5 with your chemistry. The quantum theory, which is discussed in Modules 2 and 3, which explains the behavior of light. The plate tectonics theory, which explains why the continents move. And even the Big Bang theory, which is out there to explain how the universe was created scientifically. Each one of these theories is a synthesis of large information that was tested upon by earlier hypotheses that were formulated. Okay, so that is what a theory is. It's a large body of information that encompasses well-tested hypotheses. And then you have a law, like the law of conservation of mass is an example of a law. It's a general hypothesis or statement about the relationship of natural quantities that has been tested over and over again and has not been contradicted. That is the difference between a law and a theory. So let's take a closer look at theories. First, a scientific theory is much broader in scope than a hypothesis. So I give you an example here. Let's look at this hypothesis. Mimicking poisonous snakes is an adaptation that protects non-poisonous snakes from predators. That is considered a hypothesis. We can test that. A theory would be, for this same concept, evolutionary adaptations evolve by natural selection. Darwin's theory of natural selection, which you learn about in Module 8 with evolution, accounts for an enormous diversity of adaptations, including mimicry. So do you see how that theory is a lot more broader in scope than a hypothesis, which is a little bit more specific? Second, a theory is general enough to spin off many new specific hypotheses that can be tested. And your book talks about Peter and Rosemary Grant, who for Princeton University were very motivated by Darwin's theory of natural selection. And from there, they decided to test a specific hypothesis dealing with finches at the Galapagos Island. And basically, they wanted to see if their beaks would evolve in response to changes in the types of available food. So do you see how from this one theory, it can spawn off an hypothesis that people can go and test, make observations and test? And third, compared to any one hypothesis, a theory is generally supported by a much more massive body of evidence, like the few theories that I spoke about earlier. Now, one thing to keep in mind, this is so important when we talk about how science is constantly evolving and paradigm shifts. In spite of the body of evidence supporting a widely accepted theory, scientists must sometimes modify or even reject theories when new research methods produce results that don't fit. Hence, what happened in the recent years with Pluto. Pluto used to be considered a planet. Then scientists made observations, and no longer does Pluto fit into what is deemed a planet, and the observations that are made based off of other observations of other planets. So now we have a paradigm shift from where Pluto was considered a planet, and now the body of evidence supports that it's not considered a planet. And it's the same with the geocentrism or heliocentrism. When we talk about how the Earth, at one point, they felt the Earth was at the center of the universe. And then as science advanced and scientific tools advanced, we learned that that was not true. Even though it was Aristarchus, who was a student of Plato, who first realized that. And of course, you know, he was banned. And from there, Copernicus, and from there, Galileo, who revitalized all of this notion, and we now know that the sun is at the center of our universe. So quick little question, which of these often changes over time with further study? A, facts, B, theories, C, both of the above, or D, neither of the above? If you answered C, both of the above is correct. And I know you may consider this kind of like a tricky question, but here's your explanation. Both can change. And because both can change, can we consider this a weakness or a strength of science? Before you answer that, I want you to think about this example. If everything a child holds true is unchanged when that child grows up with years of study, even with that child receiving advanced degrees, then either nothing was learned or that child was unusually gifted from the very beginning or was a part of a closed system. As we learn new information in science, we constantly refine our ideas. Likewise, with all of the fields of science. Okay, so now in understanding all of this, let's do a quick discussion. Section 1.7 discusses how science has its limitations. When we talk about pseudoscience or fake science, where skepticism and it tests for possible wrongness are downplayed or ignored. That's pretty much true for astrology. Astrology is not within the domain of science. Okay? Science, the domain of science does not deal with the supernatural or anything above considered above nature. The domain of science claims to supernatural phenomena, true or otherwise, lie outside of the domain of science. We cannot look at astrology as saying that that is true science. So what does that mean? Excuse me. Observations that can't be verified may be interesting. Astrology may be interesting. Your horoscope may be interesting and even entertaining, but it cannot account as evidence in scientific inquiry. There's nothing that we can do to test these ideas. So that is where our limitations of science are imposed because of its naturalism. Science seeks out natural causes for natural phenomena. It cannot support nor falsify any hypotheses that angels, ghosts, or spirits, both benevolent and evil, can cause storms, rainbows, illnesses, or cures. Such supernatural explanations are just simply outside of that domain of science. Now, keep in mind, there are cultures, and we do have to respect people's culture. There are cultures that still have witch doctors or still believe in certain beliefs. But according to science, we always seek out the natural cause. So section 1.8 is a really quick section, and all it does is it shows you how science, art, and religion are integrated. And we talk more about the integration or the big ideas in scientific methodology part 2. That's module 10. So science in section 1.8 for religion, it asks why. Science always asks how something happens. Religion asks why it happens, and art tends to bridge the two. It's the creative piece there. So when science and religion address their respective domains, and we talk about this when we talk about in module 4 with the Big Bang Theory, which talks about the creation of the universe, you're always going to see science and religion conflicting. The conflict between the two sometimes is minimized and sometimes it's absent, but it is there. So, but we have to respect each other's domains. So that's just, even when we talk about evolution, there's always that conflict with science and religion and evolution. Moving on to section 1.9, it goes into talking about technology. One important thing to note is technology is not science. Science and technology are different from each other. Science is concerned with gathering knowledge and organizing that knowledge, whereas technology provides the instrumentation needed to conduct investigations. And it's important that you pay attention to a lot of the scientific tools that you will be introduced to, especially during the earth science module and the astronomy module, and even module 9 with the biology. So make sure that you pay attention to the types of technology that provides us that helps to provide us with answers, because technology is an important tool. It can be used to elevate or diminish the human condition. And by that, what I mean is your book ends this chapter with a nice discussion on getting you to think about the direction that technology is now taking. It is stated that the directions that technology takes depend less on the curiosity, because remember we started out this module and this webinar talking about how our advancements in science is because of our curiosity. But now, is it depending less on our curiosity that's driving our basic science, or more on the current needs and wants of humans and on the social environment of the times? With that being said, shouldn't we keep in mind that science and technology's potential is always to elevate? But for example, There are certain circumstances where, as we advance with our technology, like for DNA, should we use DNA technology to check if people have genes for hereditary diseases? Should these tests always be voluntary? Or are there any circumstances when genetic testing should be mandatory? They're always making movies about it. You see an I Am Legend or some other film out there, Contagion, that was recently out, where there are testing where it's made mandatory to be given certain shots. Or are we taking it a bit far? Is it becoming harmful or is it helpful? And we read more about that on page 9 of your e-textbook. There's also a university when we talk about genetic testing. How far are we taking it? There's a university that is now splicing genes, and parents now maybe can choose specific traits to infuse to have a baby to come out the way that they want them to. Are we taking it too far? So these are some ideas that your textbook helps to get you to think about when we talk about technology and its advancements. Then section 1.10 moves on to talk about physics, chemistry, biology, earth science, and astronomy, and how a little bit of what you're going to be learning within this course. Okay, natural philosophy, that's what we used to call science. Today, the equivalent term for is natural science, where it used to be called natural philosophy. Okay. And so moving forward, you will be discussing in your next 9 modules physics, chemistry, biology, earth science, and astronomy. You're not going to go into each one of these areas in depth, but you're going to just kind of tread the water on what should be known, some of the basic concepts dealing with motion, force, and energy with physics. You're going to learn how chemistry builds on physics and studies how matter is put together to produce the growing list of materials in Module 5. Module 9, biology, shows how it's built on chemistry. Biology is built on chemistry and the study of life. When you're learning about these chemical processes, cellular respiration and photosynthesis, and how it helps to keep life and momentum going here on Earth. And then, of course, with earth science, you're going to be studying geology and meteorology. Why is it that the plate tectonics move, and how do they move, and how did they create mountains, and how is it that we have such natural disasters as tornadoes and hurricanes? What causes these things to happen in our world? And of course, astronomy. You're going to be taking into a realm beyond the confines of the Earth, where there's a lot of observation that takes place in our universe, and looking at different planets and seeing how they vary from our planet Earth. So this is going to give you this integrated view and how all of these concepts merge into one another, and how you will begin to acknowledge this cohesive study of and understand our natural world. Okay? So once again, the physical world integrates science. So to understand the world, we need to look at science in an integrated way. And with that being said, welcome to the exciting world of science. If you should have any questions on today's webinar, please make sure to contact one of the natural science course mentors, or if you have any questions in regards to any other of the modules within this science course. Thank you, and I hope that